All right, Cypher and Apache Spark, multiple graphs and more in the context of openCypher. My name is Stefan Plantikow. I'm team lead of the CAPS team as well as the Cypher language group at Neo4j. And these are my colleagues, Martin Junghanns and Max Kießling. And we want to talk about those things with you guys today and also give you a demo of things to come. So, I mean, we've been working on Cypher for quite a long time now. But I would say, I mean, 2017, really a lot of activity has happened in the openCypher arena. And before we talk about CAPS and other interesting things that have been announced in Emil's keynote, I think it's good to review a bit what we've been doing in the overall openCypher arena. So, in 2006, so maybe first of all, who here knows what openCypher is? Okay, that's lovely. It's almost half, I would say. So openCypher is a community effort to evolve the standard graph query language Cypher, right? Together with other vendors, with the community, to piece by piece make Cypher, which is already an awesome language for graph querying, even more useful and widely adopted by the industry. And to bring this forward, last year we founded the openCypher implementers group together with vendors like SAP, Redis, Agents Graph, which is a Postgres-based system, CypherPL, and of course Neo4j. Right. We hosted a lot of events, 3 Cypher implementers meetings, the last of which this year will be in France in November. If you're interested, we hosted the Summer of Syntax, which are regular calls for everybody interested in evolving the language going forward. We hosted the openCypher process, which is essentially happening on GitHub in the terms of writing language proposals and requests for proposals and discussing around them. We made releases of the Cypher frontend, the grammar, the TCK. We're working on formal semantics together with the University of Edinburgh. For people not that much into that world, that is something that has only happened for SQL last year, and these are the researchers that are doing it, and they're now doing it next for Cypher. So we're particularly proud of that happening. People are working on stream processing. We have been active in the standards world, both with the LDBC and the ISO, and of course we keep adding features to Cypher. The most prominent one will be featured in this talk, which is the ability to deal with multiple graphs, but we're also working on subqueries and parse patterns and many more things. So let's take a step back, right? So Cypher originally was conceived in the context of OLTP workloads at Neo4j, right? And of course OLTP is amazing, it's useful, that's what drives the web, but there are other arenas nowadays. Many Neo4j customers, they have a data lake, they use Apache Spark, and they want to do slightly different things in those contexts, right? And what you do, of course, in the context like Spark is big data analytical processing. You often have to deal a lot with data integration, or maybe you want to call it data wrangling to get your data in a shape coming from multiple sources that actually becomes useful for you, right? Those kinds of things. And just to run through a typical application, right? You do things like collecting data from user interactions at a website. Maybe you combine it with data from other departments, billing, marketing. Maybe you have some kind of knowledge graph that you need to take into account, but you want to do all those things, right? And of course, the end goal usually is you want to analyze things better so that you can target your customers more effectively going forward, right? Optimize supply chains, detect fraud, right? So we are asking ourselves the question, is Cypher ready to be used in a big data lake context? And to again maybe highlight the 2 big things that happen in this arena is of course data integration. I already spoke a bit about that, right? You want to use multiple large-scale data sets. You want to retain and reuse intermediary results. You want to integrate multiple data sources, right? And shape and handle heterogeneous data. And then the other thing that happens in that environment often that over time as you write all this business logic up, you want to compose things into complex workflows to integrate with things like machine learning, AI, graph algorithms, domain-specific business logic, right? And of course execute that then ultimately in the cluster. And because in big data it's so much about the integration of different technologies, right? The industry is increasingly zooming in on using one technology. And the technology is Apache Spark over Hadoop. So we want to bring Cypher to the wider industry, right? And to facilitate that goal, we implemented and developed for a year now Cypher for Apache Spark. Right? And we have released it last Friday in an alpha open source release on GitHub. And what is it? Right? It is a Spark package that brings Cypher to the world of Apache Spark. It enables you to execute your queries, to integrate Cypher in your Spark analytical pipelines, to access multiple data sources, Neo4j, HDFS, local file system, to deal with heterogeneous data, because Cypher as a language and in general the world of graphs is very good at dealing with heterogeneous data. It's much better equipped for that task than SQL itself. And also we're going to give composability of Cypher queries to enable powerful workflows. So yeah, we made it at Neo4j for a year now, but we donated it just Friday to the openCypher community for shared development by the wider Spark ecosystem. And of course we're going to continue to also contribute to it. It's not a done affair for us at all, right? So we now did the alpha release under Apache license 2 on GitHub. It's available, you can get it, you can build it yourself. We're targeting a 1.0 release in the first half of 2018, and we're also looking at providing commercial extensions for integrating more sophisticated data sources from our side at Neo. There are two key innovations, I mean there are many interesting things in it from us also from a development perspective, but the two key things is of course the technical architecture for executing Cypher on a big data analytical system, something we haven't done before, at least not in the way in which you have to do it in the Spark world. And the other thing of it is of course we are providing composable queries for working with multiple graphs. Right? And just to have a quick look at what the technical architecture of the system is looking like. Right, we have the openCypher frontend, the tried and tested Cypher frontend from Neo4j, that's also now available under an Apache license 2. Then we have Cypher for Apache Spark itself, which takes Cypher queries and translates them to the Catalyst query planner of Spark, right, which optimizes the queries for us beyond the optimizations that we do in caps. And then finally, they get executed as regular Spark jobs on the Spark runtime. One more thing that we had to solve, right? In Spark, it's very common to use Spark SQL. So you take a table, you run some SQL, you get a new table, and you do that all day, basically, right? That's the bread and butter of being a Spark engineer, right? So if you look at Cypher 9, the version of Cypher that we have in Neo so far, it takes a graph and gives you tabular data, right? And that's kind of where it stops, right? How can you go on from there, right? So we had to figure out how to handle multiple graphs and how to achieve query compositionality. And I'm going to talk about that next. So Cypher with multiple graphs is the hot topic. So what's that about, right? Imagine in the future you have a Cypher query, and the future is happening now, right? It happened last Friday. You have a Cypher query, and it takes a graph as input, then it filters it a bit, it shifts it around, and then it does the graph projection, it produces a new graph as output, right? And then on top of that you can continue executing, right? And in this way build really, really powerful workflows, right? And of course, this is a whole fundamental shift for the model of the language, and I'll touch on that in a second. But beyond that, there's much more to multiple graphs than just graph transformation. We see a lot of interesting use cases coming up by adding this feature to the world of Cypher. From combining and transforming graphs, to versioning and snapshotting, to access control, to application graph views, to dealing with heterogeneous data, to roll up and drill down. There's going to be a lot of exciting things coming in the world of multiple graphs in the future to both Cypher for Apache Spark and certainly also Neo. But of course, what does it do, right? It changes the fundamental model from today, where you access maybe with your graph client to a single graph, right, in Neo4j database, to a world where that database will handle or will provide you with multiple graphs, right? And of course, that raises the question, you know, what does it actually mean to compose those graphs? And what we actually discovered working on this, that graph transformation is in essence the inversion of graph pattern matching. So it was waiting all along in Cypher for us to just, you know, dig it out and make it available in a sense. So if you look at, pattern matching today, right, you have a pattern and then you find the different instances of your pattern, and then ultimately that gets you a tabular projection. But in the world of graph construction, you do the opposite operation, right? So for each record or each pattern match that you have built or maybe have transformed, right, you try to interpret that as tiny subgraphs, and then you do the union over all those tiny subgraphs, and then you have reconstructed a new graph for further processing, right? And this way, we have implemented graph views in Cypher for Apache Spark. So where does it get us, right? That gets us into a world where we can run a Cypher query that takes graphs and tabular data as input and provides graphs and tabular data as output. And then we can take the next step and just do it again and again and again. And this makes Cypher as a language for the first time fully compositional under both graph and tabular data in one platform. Right? to just give a primer on the syntax, which is not 100% finalized, which we've been working on throughout this year in the openCypher context, right? This is how Cypher may look like in the future, right? You will be able to say from graph A add, and then you give some kind of URI, which kind of identifies the graph you want to use, right? And then you get to do regular pattern matching, and maybe then you want to access a different graph in the same query, so you get to say from graph B, maybe an HDFS, right? Maybe a Neo4j, and then you do some other pattern matching, right? And then you can end your query either returning tabular results or, again, composing your tabular results back into a new graph using this kind of graph view feature that I briefly touched on here. And all this is, there's ongoing work on this. There's a SIP in the openCypher context for working on the multiple graph syntax that's massively rewritten still, so it's under active development, all of this, right? But we're adding a lot of features here. We will also look into DML and things like that, but I can't touch on this in this talk. Right? If you're interested in that, please get involved in the openCypher processes. That's not the end of things, right? Maybe want to just highlight two things, right? Graphs are addressed using URIs, right? You already saw that, and this gets us into a very extendable scheme that's well established in the web arena, right? And graphs and tabular data are parsed into and returned from a query. That gets us query compositionality. But then there's a lot of more things to come, like set operations between graphs, subqueries over multiple graphs, updating graphs, managing graph persistence, creating views, and a topic that Martin will touch on in a bit is, of course, schema and constraint definitions for multiple graphs. Right? And if you're more interested in the language side of this, then please join the openCypher Multiple Graph Task Force, which is the group that meets regularly as part of the wider openCypher umbrella activities to bring the language changes forward, right? And now Martin is going to talk a little bit about what it actually means to put Cypher for Apache Spark or Cypher the language on a relational engine.
Thank you. Yeah, hi everyone, I'm Martin, engineer at Neo4j working on CAPS, and I will talk a bit about how we map Cypher to Apache Spark. So of course all of you know Neo4j, I guess many of you know Spark, and we will start with some challenges that we have to deal with. So for example, as you know, Neo4j is a native graph database system, which means everything from the underlying data structures up to the operators for the query language are native and optimized for graph operations. On the Spark side, you have this thing called a data frame, which is basically a relational table abstraction, distributed one. And you have, of course, relational operators, as you all know from SQL, for example. Then another challenge we have to deal with is the topic schema. So we have schema optional schema in Neo4j, and we have a fixed schema on the data frame API. And the last one is data types. We have the Cypher type system, and we also have a type system in Spark SQL, and we have to translate between those systems. So I will briefly look into these challenges. So of course, you're all invited to look at the source code, which is publicly available, and also ask questions later. So let's start with the first challenge, the schema. So as I said, data frames require to define a schema. We have two ways. You can explicitly define a schema if you use, for example, our HDFS data source for the Neo4j data source, so you can import your data from Neo4j into Spark. The schema is implicitly inferred from your data. And of course, based on that schema, we can do the type mapping between Cypher and Spark SQL. So let's assume we have this property graph instance, an example for a social network. We have persons that know each other, some properties and relationships to systems. And for example, a simplified version of the schema would look like this. So we defer the node labels. We have employees, persons, and systems. And you see here, for example, that an employee is always a person, at least in this graph here. So which means we have an implied label. You see that at the bottom, that if a node has the label employee, it automatically has the label person. So this is important for the next step. And what you also see is that, for example, Alice and Bob have different sets of properties. So Alice has, Bob has the year of birth property, which means in the schema, this is a nullable property. So the next challenge we need to deal with is the representation. So on the upper side of the slide, you see the logical view. So the graph, the property graph itself, the instance, And on the lower side of the slide, you have the physical view, data frame view. So what we use is a concept called node scans and relationship scans, which are actually wrappers around Spark data frames. And for example, you can see here 2 node scans, one for persons and one for system nodes. And what you all can also see, and this relies to the implied label thing that I explained before, is that we don't have an actual node scan for employees, but it's part of the person node scan, because we can decide if a node person is actually an employee, yes or no. And what you also see is that we just store the properties in columns, so it's really a tabular view of the nodes. And you can see that, for example, Alice doesn't have the property year of birth, so it's a null value in that case. The same, of course, for relationships. Here we have additional information. Of course, we need the source and target of that relationship, so the node it comes from and the node it points to. And of course, the relationship properties are modeled in the same way. So, and these node scans and relationship scans make up a graph, and this is our input for our CAPS engine, and where we build our query plan on top of. So this brings me to the next challenge, which is translating a Cypher query into the underlying data frame API. And of course, this is again the logical view. And like I said, the node scans are the input. And what we do, we translate Cypher operations or Cypher query operators into data frame operations or relation operators. So this is basically where the magic happens. And actually, you don't need to deal with that, because you just define, as you will see later in the demo, your Cypher query, and the system translates it into a data frame job underlying. Of course, if you're interested in that, we can talk later. And the last thing I want to show you is representing results. So for example, here, when we have our graph and we have the query, the result is, as you would expect, a table which contains all the data necessary to reconstruct everything that is mentioned in the return statement. And that's what you get out of the CAPS engine after you query the graph. Okay, so let's look a little bit into the API, the basics. So we try to model our API very similar to what Spark already provides, so to make it easy for you to integrate CAPS into your existing Spark data flow. And the central entry point for CAPS is the so-called CAPS session. So this is a very basic script which actually runs in the first line. Some of you might know, if you're familiar with Spark, we just initialize a Spark session, defining everything that we need for that. And in the second line, we use that Spark session to create a CAPS session. So, and this is your entry point into the CAPS system. And in line 3, this is a very interesting thing. We say we want to work with a specific graph. And this graph is stored in HDFS. We define just a path to where the graph is stored. And that's it. The system loads it for you. And then you have the graph variable, which actually points to that graph. And in line 4, this is the first step where we actually trigger the query. So we say graph.cypher, then your well-known Cypher query, and then we say result.print to print what you would expect, basically the same output as in Neo4j. Okay, let's get a bit more advanced about data integration. So CAPS is capable of mounting multiple graph data sources, and you can use multiple data sources in your graph workflow. And those graphs coming from those data sources are stored in a so-called session local graph storage. So let's look at an example. It's a bit more involved. So for example, here in the first line, we mount a graph at a specific alias, just a mount point. So for example, here we mount a graph that is stored under the HDFS path that you see here, under the name my HDFS graph. So this is the name that we can use to refer to that graph at a later point. In the second line, we do the same, but this time we use bolts. So we access Neo4j here and load the graph from Neo4j, given two queries, one for the nodes, one for the relationships, and we store that graph under the alias my Neo graph. So now we have in our session local graph storage two graphs, the HDFS graph and the Neo graph. So now in line 3, what we actually do is we use both of those graphs to create a new graph. So we say Cypher, and in the first line we say from graph at session /myHDFS graph. So now we set this graph as the graph that we query, match the employees, and then we change our so-called source graph to the Neo4j graph and query for persons, and then we join those two graphs on a similar or the same or property. In that case, the email, which is like the identifying property for employees and for persons. And this gives us the possibility to create new edges between those two nodes, and this is the important thing. So we say here result, return a graph, and the result, this is the name for the graph that we return, of E, so the employee is the same as person. And then we can use this graph to compose it with the next Cypher query, which you see in line 4. And for example, here we just want to count the edges, but this can be arbitrary complex, what you do in the next step. Okay, you will see more of that in the demo that Max will represent. But I give you a short overview of the demo to get you started. So we are working with two artificial data sets here, or at least the left one is artificial, the right one is an actual existing data set. So we have social network data on the left, and we have so-called product data on the right. So in the product data set, we have customers that buy products and rate them, and those products belong to categories. And on the left side, we have again a social network. Friends know each other, persons know each other, and they live in cities, and they have specific interests. So what we want to do in the demo is we want to show you an example for a marketing campaign. And in this campaign, we want to target specific customers in selected metropolitan areas. Then if we have those customers, we combine those multi-regional data from the social networks with the product data, and then we want to derive recommendations. The social network is actually stored in two Neo4j instances, so one for North America, one for Europe, and the product data is stored in HDFS in our CSV format. So in the data, in the demo, you will have the following steps. At first, we load the data from these specific data sources. Then we start, we're only interested in specific subgraphs of the social network. So for example, for the North America network, we are interested in people from New York and San Francisco. Then we merge the social network data with the product data. In that case, it's the identifying property, the email. And then we can compute the recommendation based on everything that we have, right? The social network, the product data, and the newly created edge. And then we can start with the recommendation. And that is what Max will show you now.
Okay, so let's switch to our demo. So what you see here is a Zeppelin notebook. We have integrated caps into Zeppelin. For those of you who don't know, Zeppelin is a tool for data analysts that allows you to access Spark and other big data tools inside your web browser and then query your systems and get instant feedback. As I said, we have integrated this into caps into Zeppelin. So just scroll over this. So we start here by importing all the necessary libraries, and we create our cap session as Martin described earlier. I've already done this because the initialization process of Spark in Zeppelin takes a while. Then we load our data. So here, of course, we only use, for the demo, we only use a toy data set. So we have around 10,000 nodes in the social network and around 300,000 nodes in the product data. What we do here, we load our three graphs. So Martin already introduced the syntax. So we have our two social networks, from one for North America and one for Europe, and we query them from Neo4j. And here you see how we try to align with the Spark API. So also you have the cache keyword available, so to tell Spark to keep our graphs in memory. And then we do the same for the product graph, which we load from HDFS in a CSV format, and we store this product graph in the session under /products. So we can actually run this here. Shouldn't take too long. Or it does. So that has been it. So let's start with some, now that we have our graphs, let's start with some well-known Cypher queries. So this is no graph compositional thing. These are just standard Cypher queries, as you all know so far. So what we do is we take our North America social network and we find people that are located in 2 metropolitan areas, which is in our case New York and San Francisco. And we find people that are interested in a certain concept, and we want to find out how are those concepts distributed throughout the cities. So let's run this query on the North America social network and then on the EU social network. So it takes a while to start the Spark job, and the overhead for initializing the Spark job is quite large. So this is what Zeppelin actually provides you is that you can that you instantly receive the feedback and you can visualize it in certain ways. So here we have the distribution of our concept. So we have music, videos, and DVD and books, and you can see that in New York it's apparently so that people like to listen to music, while in San Francisco people watch videos. And so you have this bar chart representation, but you can also look at the tabular visualization and see the result of the Cypher queries in a quite well-known way. We've done the same for Europe, here for Berlin and Stockholm, and you see we can actually run Cypher queries on standard Cypher queries on our graphs. So let's continue to a more complex case. So this is actually now the demo that or our case that Martin just introduced, where we want to do a marketing campaign. And what we start with is, let me just start the computation here. What they actually do is, first we want to find clusters of people. So we find a person that is located in one of our 2 cities, and then we find friends of this person who also lives in the same city, and we, if 2 people know one another, we connect them via a new edge, which we call similar circle, and then we return a new graph, which is consisting of those 2 nodes and the newly created edge. So this query actually returns a new graph, which you can see here. It's quite bright, but I think you can still see, I hope you can still see it. So you actually see those 2 clusters, one for every city. So this is the cluster for, let's see, if we click on the node, you can see that it's James Williams with his attributes, and you can see that, yeah, we can scroll in and we see that we have a person, and the person is in the same circle with this person. So we have created a new graph and returned it and stored it under in a variable which we call city friends North America, and the same we did for the EU graph, which disappeared.
Social.
I don't know where it is. Let's see if it finds it now. While this computes, it's just a similar result for the North American network. There it is. So now we take those 2 graphs and we create again a new graph, which is the union of the 2 graphs we just created and all our initial social networks. And we store this graph under again in the session under /friends. And using this graph again, we can do a graph compositional query. So we start with the friends graph, which you can see here. So we say from graph friends at /friends. So this is just a shortcut for look at the session at /friends. And then we find people and store their email address and the person itself. And then we switch our context graph. So now we're not reading from friends anymore, but now we're reading from the products graph. And here again, we also have users, and they also have an email address. So what we can now do is we can combine or find links between the people in the social network dataset and the users in the products dataset. So which we did, this is what we do here with this predicate. So if a user has the same email as a person, then create again a new relationship between the user and the person an is relationship, so that states the user is the person. And again, we create a new graph from these two nodes and the is relationship. And again, we build the union, and now over our social network, over our product data, and the let me run this here. Forgot to click on it. I forgot this. Sorry. So now we have a new graph which has integrated the products graph and the social network graph. And now we can do our actual recommendation query. So what we want to do is we want to find a person which is in the same circle, so which is in the same friendship relationship with another person. And this person likes a thing, like a book or a video. And now we look for friends of this person who has bought this product. So,
if you want to do it,
and this product is actually in the same category.
I'll wrap it up at the end.
So we have a person which is in a similar circle as another person which likes an interest. And this person is the same thing as a user in the products data set. And this user has actually bought a product which is in the same category as his friend's interest. So in this case, we could assume that maybe the friend is also interested in this product and maybe wants to buy it. This is what we do here. So we apply some additional filtering, so we only want to advertise products that are highly rated and where the rating is essentially marked as a helpful rating. And in this case, we return again the standard Cypher result. So this is actually taking a bit longer because it has to take into account all those nodes and graphs that we just created. And yeah, as you can see from this demo, we have now managed to integrate two data sets that were in different data sources, so one in Neo4j, one in HDFS. We've managed to integrate those data sets, and we could use this connection between between users and people in the social network to generate an actual recommendation for products in the end. Okay. If it eventually, yeah, there it is. So now we have a tabular result where we say the user Brian Kelly, which has this arbitrary email address, could be interested in the book Life of Pi. And that's basically the demo I wanted to show you. And now back to Stefan.
Yeah, seems like that to me. Can you get me back in? Yeah, cool.
Das lief nicht so gut.
Am I on? Cool. Okay, so yeah, exciting things. Cypher for Apache Spark, right? And it's out after a year. We're all very happy having done that, actually. So Cypher is everywhere, right? And that's the message that I think was already visible in Emil's keynote. It's visible here, and we hope to make it again visible in the talk that Alistair Green and Mats Wittberg are giving at 2 o'clock around big data integration with Cypher, also in the context of Cypher for Apache Spark, but also in the context of other technologies. So if you're interested in that, please come. But that's not the only thing that's happening, right? I don't want to touch briefly on all the other subjects that we have been covering in the openCypher arena this year and all the features that are under active development. And if you're interested, you could get involved in that, right? And join the openCypher community, right? Multiple graphs we've seen. The other big topic that we're actively working on is subqueries. Cypher today already has limited support for subqueries, right? You have existential subqueries, you have pattern predicates, pattern expressions. And we want to expand on that and provide the full set of subqueries that you would expect, for example, in a language like SQL, right? In terms of having nested subqueries, correlated, uncorrelated, existential subqueries, set operations, and also certain logical operations that we think are interesting in the graph context, right? So we are actively working on that, and that will massively increase, again, the expressivity and power of Cypher. And in terms of effort, it is also not such a big effort to actually add that to the language once the design of the language feature has completed in actual implementations, right? And the other great thing that has happened this year, Tobias Lindacker has worked quite extensively on a feature that is called path pattern queries. Who here is familiar with the concept of a regular parse pattern or an RPQ query? Hands up. Okay, so if you're interested in graphs, you should maybe learn a bit about that, because what that essentially is the ability to describe which kind of nodes and relationships, or which kind of nodes and relationship labels you want to encounter as you're matching a parse using a regular expression, which massively increases the kind of patterns that you can search for in your graph. And then parse patterns go one step further actually by providing some additional tabs that traditional RPQs cannot cover. And if you're interested, have a look at the SIP, have a look at the material on openCypher.org for learning more about these features. Right, then smaller ones are aggregation and grouping. Mandatory match was recently added. It's kind of like an assertion functionality which makes sure that a certain match statement in your clause actually returns at least a single record, which can help you a little bit, make it easier for you as a developer. You have to do less checking and stuff like that. So that's more like a utility thing. Then we're looking also actively in what has now come to be known as configurable pattern matching semantics, right? Because Neo4j by default, if you do pattern matches for a single pattern, you can't match the same relationship twice in an instance, and that is sometimes what people don't want. Sometimes people want isomorphism or other pattern matching semantics. Sometimes people want, instead of matching relationship parse like we do in Cypher today, they want to match simple parse where you can't have matched the same node multiple times. Right? And these kind of things we are making more flexible with configurable pattern matching semantics. And last but not least, we're actively working on the versioning story around Cypher. So we are now looking into what is the right approach for versioning, and Mats has given recently a quite nice presentation on that. And the current thinking in the openCypher community is to say we will have major releases in multiple years increments that will provide stable bases for people to write applications against. Right? And right now we're just in the process of finalizing Cypher 9, which is effectively Cypher as it is today, and then all these interesting future features are going to become available in Cypher 10, and we're also targeting writing a natural language specification for Cypher 10, right? So we're kind of trying to step up here in terms of maturity. If you want to find more about the world of openCypher, and of course the CAPS engineers are also going to be there, join us at the openCypher meetup here in New York City tomorrow, 5:30 to 8 in WeWork Park South at 110 East 28th Street. And we will talk about some of these topics: multiple graphs, subqueries, parse patterns, connecting research and graph processing to industry, and property graphs with time. We are having a guest speaker who does amazing research around time-based property graph processing, and we're all looking forward to that as well. Summary slide, right? CAPS core alpha source releases out with multiple graphs for Christmas, right? Production ready sometime next year. Of course, we will also do commercial companion products, right? Data lake integration and other sophisticated graph data sources, right? That will come from Neo. And also Cypher programming is in the works. So Cypher is really emerging everywhere. And of course, it continues to evolve through the openCypher process. If you're interested, get involved, come to the booth here at GraphConnect or come to the meetup tomorrow, or even to the openCypher implementers meeting in November in France. And I hope you all enjoyed this, and I hope to get a lot of feedback on Cypher for Apache Spark right in the future.